Again, welcome to Business Calculus, Mathematics 200. This is our lecture 11-4, which cover our course textbook, chapter 11-4. In this section, we're going to discuss about derivatives, which involve related rates problems. So our main objective is using implicit differentiation to solve problems that involve related rates. So anytime we said the problems that involve related rates, it means something changing with respect to time, rates. So example will be a speed. We know the speed involve the distance that it travel, a car, let's say a speed of a car. The distance that the car travel with respect to time will give us how fast it's going, which is the speed. So here we say the derivative represents the instantaneous rate of change of one variable with respect to another. So even our definition of a calculus involving a single variable is rate of change of something or rate of change of a phenomena with respect to a second variable. In this case, related rates, we're mostly going to focus on with respect to time. So we say when the derivative is taken with respect to time, it represents the rate at which that variable is changing with respect to the time or the velocity. So an example here, we said if distance x is measured in miles and the time t in hours, then the s dt is measured in miles per hour. And that indicates or that represents the speed. We know a speed is measured in miles per hour. That's if the distance is measured in miles. Now, if the distance is measured in kilometers, then the speed will be kilometers per the time. Let's say the time is hour. Or let's say if the time is in seconds, then kilometers per second. So related rates is involving any phenomena, change of any phenomenon or any condition based on time or with respect to time. So for example, here we have a height of a tree h in feet. So that's the height of a tree h in feet. Is related to the radius r in inches of its trunk. So here we may say that, okay, when the radius of the tree increases, maybe the height also increase. But this also happen with related to time, because when a tree is growing up, it's with time it will grow up. But here we have the relationship between the height of the tree and also the radius of its trunk. So we have a model here, h equal to k times r to the power 2/3. K will be a constant value, and r is the radius of the tree's trunk. And based on the radius, in this case, we can see that when the radius increase, then the height also may increase. So of course, both h and r are also related to time. As we said, the height of a tree will grow with respect to time. The radius of its trunk will grow with respect to time. So the rate of change, the h dt and the r dt are related to each other. So the h dt means with the height with respect to t, change of height with respect to time, change of radius with respect to time. So these are called the related rates. So most of the examples we are going to see in this section, again, it involves with time, change of time. Again, we are going to use implicit differentiation. We already covered that section of the course. So we have the example one, the tree height and the trunk radius. So suppose that for a certain type of a tree, the height of the tree is in feet, is related to the radius of its trunk. And we have the model h equal to 15 times r to the power 2/3. So our case, a constant value in this case is 15. Now suppose the rate of change of r is 3/4 each inch per year. We should find how fast the height is changing when the radius is 8 inches. So remember here, they gave us the original function. So we need to find the derivative of this function with respect, in this case, again, height with respect to time, r with respect to time. So here we said to find how the rate, the height change with time, which is the h dt, and also how the r change with time, which is the r dt, are related. So we differentiate first, h equal to 15 r to the power to third implicitly with respect to time. So what we are trying to say is that the r varies with h, but both h and r varies with time, or they are related to time. So here we are going to find them. We are going to use implicit differentiation to find the h dt and the r dt. So first we say, okay, the h dt equal to 10 r to the power negative 1/3 dr dt. So we are using the chain rule. Let's go back to the function and we can just plug in. And so first of all, I'm going to find chain rule for h. The h equal to 15 r to the power to third. H and r, as we said, they are related or changes with time. So the derivative of h, remember h is one variable. So derivative of h will be 1 times the h dt using the chain rule. The same thing will come here, the derivative of r to third minus 1 will give us negative 1/3. Then 2/3 will be in the front. So we get 15 times 2/3. 15 times 2/3 will give us 10 because 15 times 2 is 30. 30 divided by 3 is 10. So that's why here we have the h dt. It will be 1 time, derivative of h will be 1 times the h dt. Then derivative of r, again, if it's only r, like it will be 1 times the r dt, but it's r to third. So to third minus 1 will give you negative 1/3. Then 10 and 15 times to third will give me 10. So now we know the radius is 8. So we are going to, the question gave us that the radius is 8. So we are going to use the r equal to 8 inches. Then if that's the case, then the r dt will give me 3/4 inch per year. These two values are given in the question. Because we said that, well, let's go back to the question. We said here that suppose that the rate of change of r, so that means rate of change of r, dr dt, because it's changed per year respect. So dr dt will give me 3/4. And also they gave us the radius to be 8. Okay, so right here, find how fast the height is changing when the radius is 8. So those two values are given. First, we do the implicit differentiation. H is respect to t, r is respect to t. So we use the chain rule for both of them. Derivative of h will give me 1 times the h dt. Derivative of r to the power to third will be to the to third times r to the power to third minus 1 dr dt, chain rule. So that's what we have here. So now we know the values. We plug in, r is given to be 8, dr dt is given to be 3/4. So we plug in the values. And now we have the answer for dh dt, which will give me 15/4. It's the same as 3/4. So now we know the h dt will change 15/4 feet per year, or 3.75 feet per year, because the radius of the tree trunk changes 3/4 per year inch. And we are using the radius to be 8 from beginning. So we plug in 8, we plug in our 3/4 for the RDT, and we get this. So let's move to the next section, which is the percent rate of change. The same concept, but this time is percentage. So here we work example 1, which again concerning the radius of a tree trunk and the height of the tree related to time. So we say the work in example 1 shows how to obtain related rates, but the different units. This is feet per year or inches per year. And this will be somehow difficult to interpret. So for this reason, we are going to learn how to find a percent rate of change, which is more easier to interpret, which will be whatever percent of the change in per year or per second, depends on the unit of the dt, the time. So here we say the percent rate of change of a quantity is the rate of change of the quantity divided by the quantity. So we have an example here. Poisson's law expresses the flow of blood F as a function of the radius R of the vessel according to this model. So F equal to K R to the power 4. F is the flow of blood, the rate of flow of blood, and the K is a constant value. R will be the radius of the blood vessels, or the radius of the vessel. So K is constant. Now, when the radius of a blood vessel is restricted, such as by cholesterol deposits, drugs can be administered that will increase the radius of the blood vessels and hence the blood flow. So we can see from the model here that if the radius of the vessel is less, the blood flow also will decrease. So that's why when we have an issue with this cholesterol level is very high, we take a drugs to again remove it. So here they say we should find the percent rate of change of flow of blood that correspond to the percent rate of change of the radius of a blood vessel caused by the drug. So here we seek the percent rate of change of flow. So that would be dF dt divided by F, because it's percentage. So previously, when we find the h dt, if we divide the h dt by h, that will give you our percentage rate of the height of the tree growth per year. So that's the formula. So now we already know the steps, how we can find, again, F is related to T, R also the same. So we are going to do implicit differentiation. So we get 1 times the F dt, the K is constant, then we get 5, we get 4 times R to the power cube, so 4R cube. Then the R dt also, both are related to time, dt, dt. Now, based on the question, they will give us the K. If they don't give us the K, then we're just going to find the model. Or they can give us the radius and the K, then we can find the flow of the blood, rate of flow of the blood. But in this case, we're just looking for the model. So to find the percent rate of change of flow, we are going to divide dF dt by F. So the equation will look like this, dF dt by F. And if I divide the left side by F, I have to divide the right side of the equation by F also to balance it. So 4kr cubed dr dt over F. So if we replace F on the right side of the equation with F, remember F is equal to kr to the power 4th. So we replace it. Then we cancel some few things. K will cancel the K, R4 with R3, so remain 1R added down to be 3 minus 4, negative 1, so it will go down. So this will be our equation. So if the R dt is given and R is given, we can find the percent rate of flow of the blood. So here we see that the percent rate of change of the flow of the blood is 4 times the corresponding percent rate of change of the radius of the vessel. Again, they didn't give us, but we know it's 4 times dr dt. Dr dt divided by R is also the percent rate of change of the vessel, the radius of the vessel. And the F dt over F is the percent rate of change of the flow of blood. So that will be the interpretation of it. Now we have a question here. They say this means that a drug will cause 12% increase in the radius of blood vessel at certain time, it will produce a corresponding 48% increase in blood flow through that vessel. If we have 12% increase, then that will also increase the blood flow by 48%. Why? Because 4 times 12, as we can see the equation, let's go back one more time. Here we have 4 dr dt over r. So dr dt over r is percent rate of change of the radius. df dt over f is the percent rate of change of the blood flow. So if dr dt over r is 12%, 4 times 12% will give me 48%. So it's 4 times more of the radius. So we can see it's more easy to interpret than if we are using only the rate of change. So percent rate of change is very straightforward to understand. So next is solving related rates problems. So let's see this example. For some problems, the original equation relating the variables must first be developed from the statement of the problem. So first we need to develop the previous example we saw, especially the example number 1, we can see the model is given to us, the equation is given. But sometimes we may have a question where we have to develop our own equation. So this is a very good example here. Now, this is the procedure to follow to solve a related rate problem. A question is given. You can see in this question, we don't have no model. They say the sun falls at a rate of 5 feet cube per minute on a conical pile with the diameter always equal to the height of the pile. At what rate is the height increasing when the pile is 10 feet high? So that's the question. They didn't give us the model. The previous example we saw, actually 2 examples, the model was given to us. Now, when we look at the question here, they are saying that cone is conical pile. So that means the shape of this object is a cone. And they are dealing with the volume. So first, use geometric and or any physical condition. In this question, we are dealing with an object, so it's geometric formula. So the conical pile has its volume by V equal to 1/3 pi r square h. This is the formula. Now, most of our questions, we are going to give the formula in the question. Now, next, we're going to substitute into the equation values or relationship that are true at all times. Based on the condition given here, we can say that the radius r is half the height at all times based on the question. So r equal to half h at all times. So what I'm going to do, I can substitute the r with the h formula. So it will be half h square. R square will be half h square. Because the question says, at what rate is the height increasing when the pile is 10 feet high? Now, if they say at what rate is the radius increasing, then I'm going to change h to r. So yeah, we want to have only 1 unit based on the condition. Because yeah, substitute into the equation values of relationship that are true at all times. So now our formula will be pi over 12 h cubed. Next time we're going to do, now this is the model we are going to do based on the condition V equal to pi divided by 12 h cubed. So we're going to do implicit differentiation now, which will be 1 times dv dt pi over 12 times 3h squared dh dt. And that's what we have here. So they say differentiate both sides of the equation implicitly with respect to time. Again, our topic is related rates, always with respect to time. So that's what we have. Then we substitute the value that are known at the instant specified and solve the equation. So we know dv dt is 5 at all times based on the condition. The sun falls at a rate of 5 feet cubed per minute. So we know dv per minute, so the dt, volume, feet cube. So we substitute the value 5 equal to pi over 4. The h value is 10. So 10 square dh dt. So now we can find our dh dt. So from here, we can again find the dh dt. So another question here, we say a hot air balloon has a velocity of 50 feet per minute and is flying at a constant height of 500 feet. An observer on the ground is watching the balloon approach. How fast is the distance between the balloon and the observer changing when the balloon is 1,000 feet from the observer? So in this question again, they didn't give us any model about the hot air balloon velocity with respect to time. In this case, it's in minutes. They did it. We have to look at the conditions of the question, then we have to come up with what formula, whether it's geometric formula or physics formula, medicine, medical, biology formula, whatever the formula is. But looking at this question, we are talking about velocity of hot air balloon. So this is again physics. The previous question is based on the volume of a cone. So that's a geometric formula. And as I said earlier, in our final exams, again, the formulas will be given. So here we come up with the idea. Based on the condition, we know the observer is 90-degree height. So we say if we let R be the distance between the balloon and the observer, which will be right here, the balloon to the observer, and then let S be the horizontal distance. So observer to the balloon, horizontal distance up to where the observer is, then we bring it down, because that's when they say the balloon is 500 feet up height. So based on this, we are looking for the R. So based on this, we can come up with the Pythagoras theorem. S square plus, plus 500 square equal to R square. Now, because the distance S is decreasing, we know that the S dt must be negative. So we have the S dt to be negative 50. They gave us to be 50, but because distance is decreasing, it's going down, so it's negative 50. So we have the negative 50 already for the S dt, and the R dt when R is, so we're looking for the R dt when R is 1,000. Also, that value is given to us, as we can see. They say how fast is the distance between the balloon and the observer changes when the balloon is 1,000 feet from the observer. So it's given. And also the hot air balloon has a velocity of 50 feet per minute and is flying at a constant height of this. So we have the values now. So let's find the Pythagoras theory, S squared plus 500 squared equal to R squared. We have 2x ds dt plus, this is constant value, so everything here is 0, equal to 2r dr dt. So this is it. Constant values, derivative is 0. Remember, we already know the s dt to be negative 50, so we can plug it. Also, we know r is 1,000, so we can find dr dt. And that's what we did here. We plug in the value. So dr dt will give us negative x over 20. Then we plug in the values, r equal to 1,000 in s squared plus 500 squared and r squared. So we look for the x. S squared will give us this, square root of it will give us this. So we plug in the s value, then we find the r dt. Again, r is given to us. And so if we know r, we can find x, s squared plus 500 squared, r squared, the original equation. Then when we get the value, we plug in the s value, we plug in, and this is our dr dt. So finally, the answer will be negative 43.3. This means, again, the distance is decreasing. The distance is decreasing at 43.3 feet per meter. So that will be the conclusion for these lectures. Again, if you have any question about these lectures, you can post your question in the Blackboard online, or when we have a class again, you can come up with your question, or you can again post your question in the message or the discussion board. So again, wish everybody the best and thank you for your time.